All right, do we have sound? Let's have a sound. All right, so 1.6 is two-dimensional figures. All right, so the first thing we do have the word in here is curves. Okay, so our first definition here is for curves. All right, so curves are a continuous set of points. They're two-dimensional and they're planar. Bless you. All right, we have closed curves. Closed curves end at the same point where you began. So we've got a circle, right? You've got that there. And like this figure 8, they're closed. They have an end at the same place they start. Simple circles never cross. Okay, so our circle never crosses. This is just a simple curve, never crosses. How about this one, this figure 8? Is it a simple curve? No, because it crosses. Okay, so it's not simple. These are just some ways to describe the curves. All right, next up is a circle. So a circle is a set of all points in a plane, a given distance from a given point, the center. So all it's saying is that all the points out here on the outside of the circle are the same distance from the center. They're all the same. It's just a weird definition. We denote a circle with a circle and a dot in the middle of it, and we read that as a circle. So over here, this part is circle C. Radius equals segment CB. So we're bringing in some of that vocabulary that we've been using. All right, so example 1. Can a circle be classified as the following? So is a circle a curve? Yes, because it ends, right? It ends at the same point where it began. So this is yes. Is it simple? Yes, because it never crosses. Perfect. Is it closed? Yes, right? It's also closed. So a circle can be described as a simple closed curve. Ta-da! We good so far? I like it. Always good. Now, a circle divides a plane into 3 disjoint sets. So remember how a point divided a line into 3 disjoint sets? You had a segment on the left and a segment, or a half line on the left and a half line on the right, and then you had the point. Pretty much everything is going to divide into 3 disjoint sets. Okay, so it's going to have the points on the circle. So the outside is 1. The points interior of the circle and the points exterior of the circle are our 3 disjoint sets. And so if we think back when we had a line, okay, it's kind of the same idea. We had the point was one place, we had the half line to the right or the left, and then we had a half line to the other direction. So we had 3 disjoint points. When we had a plane, if you recall the plane, so that's my lame goal here of a plane. Okay, so in a plane, we had the line was 1 disjoint set. There was the half plane on one side and the half plane on the other side. So if anything, just remember that. If anything, like if it's being divided and it says how many disjoint sets, it's pretty much always 3. Okay? All right. So let me erase some nonsense there. Okay, the next thing, okay, so the circle, let me go back here, divides the plane into 3 disjoint sets, which we saw over here. And then it's true of any simple closed curve. So if it's an oval and it's not a circle, right, it's the same thing. It's going to be 3 disjoint sets. Doesn't matter. Next up is a region. Our next definition is for a region. So the region is the union of a simple closed curve and its interiors. Or sorry, its interior. Curve is the region's boundary. Let me erase this. So the region is a union of a simple closed curve and its interior. So if I were to look at my circle up here, okay, the region is the union of the curve and the interior. So there's the region. Okay, so circular region. We might have a rectangular region, but it includes all of it. The curve is just the boundary. It's like the outside edge. All right, so any set of points can be classified as concave or convex. These are terms you've probably heard in other classes. So the first one that we're going to look at is convex. Convex, V-E-X. So that's where every segment with endpoints in the set is completely contained by the set. So like a circle. So here's the thing. Okay, it says endpoints in the set. So I have endpoints here and here. They are completely contained. So if I connect them, the connection is inside the circle. It's inside my shape. It doesn't matter where I make my circles, my points, I can connect them inside. Like, yes, you always do to make a line. But I'm just saying, it doesn't matter what endpoints I pick, the segment is always inside the boundary of the shape. So it's always inside the circle. Versus the concave one. Okay, so that is when a segment can be drawn whose endpoints are in the set, but the segment is not in the set. So let me slide my paper over a little bit so we can see that. So see this shape? I picked an endpoint here, I picked an endpoint here, and I drew my line. This is outside my shape. It's concave. It's outside my shape. It can be a rectangle. I mean, like, it can be a shape like this. Okay, if I pick this point and I draw my segment, it's outside my shape, so it's concave. This is true. It would be. All right. So do convex and concave make some sense there? Yes. Perfect. I feel like we're making progress. All right, next up is a polygon. A polygon. Let me just move our paper up so we can see them. Endpoint. That's an ENDPT. That's my abbreviation for endpoint. Good. So yeah, polygon. Simple closed curve made of only line segments this time. Right? Only line segments.
So is there a shape that involves this curve and a line?
Yeah. Like this one does.
Well, like, what is it called?
Not a polygon?
Not a polygon. You got me there.
I'm like,
that is what it's called.
That is like like when you're classifying them, that's it. And so it only has line segments, and so we call those sides. And each endpoint is a vertex. Like this is probably vocabulary you already know from algebra. So example 4 says determine whether each figure is a polygon. A. Yes, it is. We know B is not because it's got this curve in it, right? So that's a no. Yes. Okay. C is a yes. Why is D a no? Right, because it said it had to be a simple closed curve, and this is not closed. Good. Right, and so it is confusing that it says it's a simple closed curve, because when I think of curve, I think of things that like look like circles, right, that are not straight segments. But a curve was really just a continuous set of points. That's a geometric definition of a curve. Continuous set of points. It's two-dimensional and they're on the same plane. So that's totally a curve in this, according to this definition. All right, flip on over to the back. Okay. Next up, For our 2 pages today, you're right. Is an equilateral polygon. So, like equal, right? Except it's going to be an I in there. It's EQUI, equilateral. I'm sorry. All right, and then lateral. So equilateral polygon. I'm going to have to curve mine. My writing on the board is larger than my writing on my paper. That's okay. So equilateral polygon is when all sides are the same length. Okay? Sides are the same length. So what is it when the angles are the same measure?
Square.
No, it's still a polygon. We're still talking about polygons, but notice this one was equilateral. Lateral is another word for side. So the sides, lateral, were equal. And then when the angles, it's equiangular.
Oh my gosh.
I know. So an equiangular polygon. Okay, is when all the angles are the same measure. And the last one is called a regular polygon. I know, right? Who would have guessed something so simple? So a regular polygon is when all the angles are the same and all the sides are the same. It's considered regular. So a stop sign is a regular octagon because all the sides are equal. A square is a regular quadrilateral. Right? So a square is regular. A rectangle is not regular. A square, a regular polygon, all the sides have to be the same length. So a square. Okay, what's the question about equiangular? Oh, okay. Nope, you're good. All right, so then over here we have all the names of all the different shapes that you might have with sides. Okay? So if you have a 6-sided shape, what's its name? Hexagon. Okay, what if I have a 10-sided shape? What's its name? Decagon. How about if I have a 20-sided shape?
N-gon.
So we would say 20gon.
Okay.
20, like 20gon. So if it's, that's true, right? It is. It's in. So whatever in is, we put in there. So if it's 20, we would say a 20gon. 30, 30gon. 31, 31gon.
32-gon.
Right. All right, so example 3. Classify each polygon by the number of sides. State whether it's concave or convex region, whether it's equilateral, equiangular, regular, or none.
Those just look like abstract drawings with all the lines.
They do, kind of, but hopefully we know what they mean.
The curves are the angles.
Yeah.
The curves are the angles.
The little lines are that what same lines are the sides.
Yes, good. Very nice. All right, so what? So that's it. What kind? What? How many sides does it have? It's 7 sides, so it's a heptagon. Okay. All right. So is it concave or convex?
Concave.
Why is it concave?
Because if you put a point right there and a point right there, then
All right. So it's concave. Good. And equilateral, equiangular, regular. Okay. Good. It is equilateral because all the sides are the same measure. Good. Not equiangular because they're different, right? These have 1. These are all the same, but that's different than the 2 up there. Good. So definitely not regular. How about B? Quadrilateral. It's got 4 sides. How about concave or convex? Let's do that one next. Convex, because no matter where I put points, right, I can connect them. So it's convex. How about then equilateral, equiangular, regular, or none? None. All right, awesome. That's an N there. Very good. How about C? How many sides does C have?
1, 2, 3, 4, 5, 6, 7, 8. An octagon.
8 sides, so it's an octagon. Yep.
Oh.
It's the little lines. That's all the little lines.
Okay. Concave or convex?
Convex.
Convex. Excellent.
And it's regular.
And it is regular. Why is it regular?
Because they're all the same. All sides and all angles.
All sides and all angles are the same. Excellent job. Very good. Hey, hey, hey. Shh, 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 shh. Shh. Be nice. Be nice. Okay. I believe you. All right. Next up. Shh. All right. Polygons are named by listing their vertices in consecutive order. So you can go clockwise or counterclockwise, but they have to be in order, whichever way you decide. Okay. The other thing, angles BE, or segment, sorry, BE and BD are diagonals. Hold on, we didn't get there. I skipped a spot. Okay. So, that's what we skipped, is I skipped it, so I'm sorry. So diagonals are any segments of a polygon connecting two non-consecutive vertices. So BE and BD. So can we, and then it says, are diagonals, any others?
A and C, A and D.
Okay, so not A and C. It would be segment, say segment AC.
Segment A and C.
Okay, no, not A and C.
Sorry. Segment AC.
Good. Can you give me another one?
Segment AD.
Segment AD.
Segment EC.
Segment EC.
Yeah. And
Okay.
now you have a star.
And now you do have a star. Okay. But all of those are diagonals. We've connected all the points that aren't consecutive, all the vertices that aren't consecutive. Okay. You got work to do, right? Oh, the answer keys for your work are also back on the counter back there in the blue folder. Awesome. You got them all. So then, how would we name this polygon, right? We're named by listing vertices in consecutive order.
A, B, C, D, E polygon.
A, B, C, D, E polygon. Okay, so A, B, C, D, E. What's another way you could name it?
A to E polygon? Like A dash E polygon?
Nope.
No, because
It says all the stuff in the middle.
But you could go AED, AED, B, or CB. Pardon me, yeah, CB. Now, I wouldn't personally name it that way.
No, that's goofy.
Because it sounds weird, right? But it does say we can go, if we start at A, we can go clockwise or counterclockwise. But like if we start at A, we could go this way. I wouldn't personally name it that way. But if you wanted to, you technically could. Okay, there's lots of different ways. All right, next up. Each vertex or angle of a triangle has a corresponding opposite side. Okay, so the side opposite of angle A. So here's angle A. The side opposite is segment BC. You see how that's opposite of it. It doesn't, it's the, because this line, segment AC touches the angle, AB touches angle A. So it's the only angle that doesn't touch is its opposite. So Justice, what side is opposite of angle B?
None.
Nope, that's not true. Every angle has an opposite side.
Oh, would it be C?
A side, you have to give me a segment. C is a vertex.
What?
I know.
AC, yes,
Oh.
it has to be a side. So it's segment AC.
I knew that.
All right, and then for the next one, it says what side is opposite of angle C? Well, here's angle C. So segment AB. Good. Is opposite. Very nice. All right, theorem 1.6.1. I'm sorry that I deleted that, and you have to write it, but I guess that's what we're going to do today. All right, so the perimeter P. So the perimeter P of a regular n-gon, so this is a regular polygon of any size, okay, with sides of length S, can be found using P equals N times S. This was our warm-up, like what was the perimeter of a square? But this works with any, this is saying the perimeter of any regular polygon. If it has 6 sides, then P would equal 6 times S if it was a hexagon. If it had 8 sides, P would equal 8S if it was an octagon. If we know one side length, we can know them all. Treasure, are your eyes bothering you? Okay. So does that make sense for this theorem? Okay, then go to your next. Okay. All right, so let's look at example 4. Find the perimeter of each polygon. Okay, so we talked about perimeter. What do we do for perimeter? We add them all together. So P equals 4 plus 10 plus 8. So 22, P equals 22 what? Centimeters. Glorious. All right, how about the next one? Let's use that theorem we just learned because these sides are all equal to 9. How many sides are there? 5. So P equals 9 times 5, which is no, 45. What's our excuse me, what's our unit there? We don't know. So we just leave it at 45. You can just leave it as 45. That's fine. If there's, but I want you to know, if a unit is listed, the unit needs to be in your answer. If it's not given, it's totally fine to leave it out. Mm-hmm. Right. Well, I had to think about what he was saying. Okay, next up is a chord. C-H-O-R-D, like a chord in music, is how it's spelled. A chord is any segment whose endpoints are on the circle. So BC is a chord. Segment BC is a chord. Mm-hmm. Segment DA is also a chord. It's got another name, but it's also a chord. OE is not a chord, right? It's endpoint. O is the center of the circle. So it's not, OE is not a chord. Does that make sense? So maybe we should write that in there. Segment OE is not a chord. All right, next up is diameter. Okay, so it is a chord that contains the center. So it's more specific. So DA, right, that is an A. Yes. So DA is a diameter. It's also a chord, but it's a diameter. Not from middle to middle. It goes through the middle. Yep, it's from... BC does not go through the middle. See, because the middle of my circle is O. That's my center.
Will all the circles be shown middle for us?
I think most, no, if like you need to know it, it'll show you the center.
Okay.
Yeah. Mm-hmm.
I mean, it's not hard to find the middle.
Right, but still. And then you have the formula here, D equals 2 pi times R. What does the D stand for? Diameter. What's R stand for? Radius. Okay. What is so the diameter of the circle goes all the way across. What's a radius of a circle? Halfway. So like OE would be a radius. Okay, if DA is the diameter, OE goes from the center to the outside edge, to the boundary. That is a radius. All right, the last one is an arc. Spelled differently, A-R-C, arc. Good try. So arc is a curve that's a subset of the circle. So I'm going to erase my stuff here so we can reevaluate. So AE is an arc. It's just a subset of the circle. BD would be an arc. And notice how we notate that. We've got a little arc, a curved line over the notation.
So would BC also be an arc?
So BC, segment BC, okay. Yep. Pardon me. Now there is a line. Let's just do this. And we'll try to erase again. Okay, so there's two different things. So segment BC would be the segment, whereas arc BC, that's a weird B, would be the arc. So there's two different parts to it. That's why notation is so important. Is it a segment or is it an arc? Good. All right, the next theorem, 1.6.2. Says the circumference C of a circle okay, so we're going to get a formula here again with a diameter D or a radius R, because you can figure these out, can be found using C equals pi times D or C equals 2 pi R. So we're given two formulas there to use. All right, if you've got that, you can go ahead and try example 5. Or you could go ahead and work on your own. Oh, you all don't have the on your own on your. Okay, I wrote them after I made copies. I couldn't remember. Doggone. Okay, we ready to try 5? Okay. So find each missing number. Okay, so, or each missing measure. So what's missing here? Well, no, we know pi.
Oh, yeah, we do.
The radius, we don't know what the radius is, right? We have it labeled, but we don't know what it is. So we have to use the formula for circumference, though, because that's what they gave us. So we know C equals, what formula are we going to use? 2 pi R. What? A calculator for this? No, we're going to leave it in terms of pi. No, we're not going to do it. We'll leave pi always. Okay, so what can we put in for C? 10. So 10 equals 2 pi R. How are we going to solve for R?
You bring the 2 over.
How do we do that? No.
Divide.
Divide. Okay. All right, so then we're going to have 5 equals pi R. I need to get r by itself. How do I do that? Divide. Okay, so I'm going to divide by pi. So my answer is 5 divided by pi equals r. You're going to leave pi in your answer. There's no reason to do anything else. Yes. Do what? Yep. All right, how about B? The circumference of a water tower that measures 60 feet across. Okay, good. 60 feet across. That's diameter. So we're going to use C equals pi dot times diameter, which is going to be 60. Okay, so pi times 60. And so that's my answer. I would say C equals 60 pi. We would put the pi after. And then what's the unit of measurement? Feet. If you wanted to do the workout, it would be approximately 188.5 feet. No reason to lie. That's okay. Yeah. Or if you use it as a fraction, it's 22/7. But, okay. So, yeah. I know you don't have that. This is the on your own. Just a second, though. Yeah, that'd be fine. We can do that. I'm trying to get the... Okay, trying to get this stopped.